this conference is really about bringing together industry, academia, and government together. That's kind of how you drive this change. You know, historically, it's always been NASA government funding that's been leading the space industry, but there's been a massive shift. And what I personally find fascinating is the amount of investment that's going into this industry, but then also the number of startups and organizations that are coming into this. So throughout the rest of the day, we are going to be talking with some of these folks from industry, government, and academia. But I'm excited to introduce Marshall Porterfield with Pulsar Exploration Industries. I had the pleasure of meeting with him a couple of months ago. Fascinating what he's leading on. Great thought leader, and I'm excited to welcome him to the virtual stage here.
Thank you, Andrew, and also thank you to President Armacost and Senator Hoeven. I hope you get a chance to stick around. Senator Hoeven, I have some information I'm sure you're going to be interested in. So I'll tell you a little bit more about myself. I'm currently serving as the Chief of Science and Engineering for Pulsar BioAstronautics, company founded based on the existing gaps that exist in human exploration, the exact goals that the senators spoke about previously is what we're focused on and the gaps in those goals. I'm currently a professor at Purdue University. I previously served for 5 years as division director for space life and physical sciences at NASA headquarters. And so part of my talk is going to be drawing upon my experience with NASA, and part of it's my experience with in academics as a professor, but now I'm bringing in the commercial side. So I'm really excited about this conference. I'm really excited about the opportunity to reach out and interact with some of the students. The students are really important to me in all of this. Bioregenerative life support, agriculture into space really is the cutting edge of space. This is where the gaps are. We're really transitioning now into a new era of space travel, but we're really going back and drawing upon some ideas that have been there all along. And that's really the idea of controlled ecological life support. This is not a new idea. Actually, there are books, literature, go back to the 1870s, actually 1880, novelist Percy Gregg published a book, Across the Zodiac, which totally describes controlled environment, agriculture, and bioregenerative life support. It's not a new idea. K.E. Skrzydlowski, a Russian scientist and author, wrote a book also around the turn of the last century, and by 1926 it actually written an entire plan that became the roadmap for a lot of what became the Russian space program in the later on in the 1960s. After Sputnik, the Russians started the Institute for Medical and Biological Problems and the BIOS programs, and that all came from this work from a really long time ago. So the U.S. has had a program called the Controlled Ecological Life Support Program. Of course, a lot of us know about the Biosphere program in the United States. The European Space Agencies operated the Melissa program, the longest running, currently running bioregenerative life support program, and the Japanese have also done this in the past too. And again, it's all about the idea of using plants as the core, our agricultural foundation for our life support system. And art and literature have stimulated people through the years. For me, I became really interested in this once I realized that plants were going to be needed, going to be the core of bioregenerative life support. I know the exact time I got this idea because it was the season premiere of Star Trek: The Next Generation. In that first episode, Captain Picard goes and visits the hydroponics deck. And when I saw that, I immediately rearranged my entire future, focused on that idea that we are going to be going back to the moon one day, and they're going to need plants to do it. We're going to have to do it in a new way. Really, this new era of bioregenerative life support. That was really catalyzed my imagination. And from that point forward, I really changed my perspective on what I did in school and became focused on opportunity to do space biology one day. And I was really lucky in that I was able to meet Mary Musgrave at Louisiana State University, and she became my major professor. But again, Now we're at this new era where we're actually transitioning from transportation to human habitation. We really focus on human health and agriculture and integrating this into environmental systems. There are two main gaps. The first gap is human spaceflight countermeasures. At the top of this list is really food and nutrition. How do you feed people? There's really this kind of a logistics problem. This is a part of the distance challenge associated with spaceflight, and that's really why we need bioregenerative capabilities in order to regenerate food, the atmosphere, everything that humans need for human productivity. So really this is about merging human medical systems with human environmental systems in terms of bioastronautics. So really it's not a new idea, it's an old idea again, but way we are implementing it is different, because what we see is we can integrate all the biology within the habitation system, the humans, agricultural systems, and all the microbial systems using omics capabilities and GeneLAB capabilities that were originally developed as part of NASA space biology programs when I was at NASA headquarters. During my time at NASA headquarters, I oversaw really the astronaut genomics and the initialization of the twins program, and also NASA GeneLAB, and a whole force move into omics technologies. And again, these are going to be applied and allow us to develop bioregenerative life support systems based on agriculture. Agriculture has to be the core consideration for long duration human exploration, really endurance class human exploration, moving away from we got a tent and a cooler in the back of a pickup truck and we're going to go to the moon and plant a flag and run back, versus we're going to go there and stay there. And that's really the shift in the thinking. And it has huge challenges behind that. Really, these are the challenges we've been avoiding. This is the hard part. Building the rockets and building the hardware, the transportation systems was relatively easy compared to the challenge we have now. But to really understand that challenge, I think we need to go back and understand a little bit about space history. When I teach space biology and medicine class here at Purdue every semester, I spend the first 2 days talking about the space race and Sputnik and the Sputnik moment. For people who lived through that time, they know that Sputnik totally changed our society. Students who left school in the summer of 1957 returned in the fall of 1958 to STEM. There was no STEM before Sputnik, basically. That NASA was founded within a few months of Sputnik. So this was a major catalytic event leading up to ultimately the moon landing and us accepting the challenge. And we benefited from all the commercial spinoffs because we accepted this major challenge, regardless of the cost. We created all these new opportunities for our economy, and that's the spinoff effect. And people trying to replicate the spinoff effect, but without accepting the challenge. And that's really one of the problems that we face. The other problem is that this space race never really ended. It was really not about the moon per se. There's a longer term space race. And the Russians were already playing that, because in the 70s, leading up to Mir, they had 3 other space stations. So they already had a space station program. They already developed in 1963, started their own bioregenerative life support program on the ground. So they were basically putting together habitation technologies and leading towards that. So the space race wasn't over. Even though we were participating and collaborating on the International Space Station, the United States was not doing the bioregenerative life support research it should have been doing at that time. Up until about 2004, we had a major program. Office of Biological and Physics Research was about $1 billion a year and included bioregenerative life support programs and the controlled ecological life support programs that NASA operated. Those were all cut in 2004. After they were cut, those facilities were actually destroyed, and all that research stopped by NASA, but the Chinese picked it up. And they completed the first trial of their Beijing Lunar Palace in 2018. And then recently completed their space station construction initiative. And they still have a second space station on the ground as a backup. They're going to fly that also. And they've also announced this major lunar program. So we are in a space race. The problem is it never stopped. And we cut all the major programs in 2004 that would have developed bioregenerative life support, which we would have had now. We cut those programs. The Chinese took all that research and all that momentum we had at that point and completed what would have been the bioplex. So let's take a look at the original biomass production system at Kennedy Space Center. You can see here's the bioplex. It was the original vacuum chamber that the Mercury capsule was tested in. And so much work was done at that time in terms of all these new technologies leading up to bioregenerative capabilities. While those programs were cut in 2004, some of that trickled on, and we've seen some of that program over the last few years, but really essentially almost over a 20-year program, the CELSS program that was cut, and the bioplex down here that was basically cut off and never completed by the Chinese in the Beijing Lunar Palace. So much was done in the CELSS program at the time at Kennedy Space Center. The first hydroponics, LEDs. I was a graduate student. I worked there. I got to work on the first LEDs, advanced hydroponic systems. We got to work on this particular flight experiment, the astroculture experiment with the first LEDs and hydroponic systems in space, working with people like Bob Morrow and Ray Wheeler. And this was really the first flight experiment with the classic purple LEDs, which has now become the foundation of the controlled environment agriculture industry. So really, essentially, we're transitioning now. We have these core technologies. We can build bioregenerative systems in terms of the hardware systems and a lot of the technology, but what we don't know how to do is integrate all this together. And that's really where my experience at NASA and with regard to omics and GeneLAB comes into play. We're really integrating human biology, microbiology, and crop system genetics within a single system called GeneLAB. And this is based on integrated omics capabilities. And this should all be delivering full-scale technology habitat demonstrations. We need to be thinking about and actually building a space station here, test analog facilities to do full testing and full flight simulation analog test with all of these systems. Again, this is addressing the human spaceflight countermeasures issues and also the sustainability issue. How do we actually logistically support spaceflight and actually do it in a way that's economically and physically sustainable? So there are a lot of remaining biophysical gaps and really information gaps, technology system gaps that are key. And we're looking at those roadmaps in terms of Moon and Mars. Project Submarine is our program to build Systomics and universal bioastronautics capabilities. So this is healthcare, microbial monitoring, and crop diagnostics all in one system. It's really an integrated human habitation system approach that integrates everything that's living within the spaceflight environment and encapsulated in the concept of bioastronautics. So Pulsar GeneLAB is that platform, both for personalized medicine and precision agriculture. Key aspects of this are the AI and machine learning tools that we're developing now, and the system level microbial ecology and precision medicine approach that we're developing. And again, this is important because even in terms of bridging low Earth orbit commercial, the tourist destination are going to require a medical and medical flight operations. So we have a clinical health and human operations program designed to address that. So again, the technology, the original idea is to really kind of duplicate the functions of the Earth in terms of life support, but within an engineered system to support human exploration. So this is really a tremendous challenge. There's a lot to be done between now and those types of systems in the future. I do see us going back to the moon first and really developing and perfecting our ability to do human deep space habitation. There's a lot of challenges with the radiation environment beyond low Earth orbit. When we move out into the moon, or especially out to Mars, that radiation exposure is going to be much greater. but I do eventually see us commercial and government coming together and forming the foundation to basically live and operate within the near low Earth orbit environment and the lunar environment, such that we can build the infrastructure to actually push people out to do more exploration. That's what I'm about. That's what I believe in, is deep space exploration and projecting human civilization and human exploration out beyond the current limits. So that's part of just a little bit about Pulsar and what we're doing. Again, a lot of this is coming from my experience as a researcher, as a NASA researcher, and also my time at NASA headquarters. But really, this is all about enabling human potential, and that human potential in terms of space exploration. So I have a great team behind me of people that are also behind human capabilities. So that's all I have. This is really a wonderful opportunity. I want to point out that from the very beginning, when I was an undergraduate student, I knew that the technologies we're developing to advance human exploration were also so important towards sustaining human life here on this planet and bioregenerative capabilities that we need desperately in our lives here on the planet today. So I will stop there with that, and thank the audience and thank the organizers for this opportunity. And I'll leave you with this last message to think about to emphasize the importance of this work. Thank you so much.